Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9 out of 24. Okay, how many of you don't want to start from uh, maybe the starting and wanted to start from BFS? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 1, 2, 3, 4, 5, 6, 7. So this was a bit manual work I have to do. Okay, there is no algorithm for me. Okay, so from the starting, uh, the people who has raised from the starting has won by 2 votes. So I would like to start from the start. Okay. So for the other people, it might be like an repeating kind of thing, but please bear with me for 1 hour or such. I will quickly try to cover the basic stuff, and then we jump into BFS, DFS, and and we will finally end with topological sorting. Okay, and after that, I will end with the week 9, the person who has week 9 doubt. I'll take that doubt and we'll end this session. So this is my agenda. I would like to repeat what I said now. So I will be starting from week 10, which is graph theory. Okay, I will start from what a graph is, and then I will discuss this week 10 contents briefly till BFS, and then from BFS I will discuss in detail till topological sorting, and finally I will end this session by taking the doubt of week 9.
Sir,
Is that clear?
in week 10, DFS is last topic or something else is there?
Topological sorting, I said, right? Topological sorting. So
Oh,
till topological sorting we will do.
How long is the session for, sir?
2 hours, and we
Okay,
will
sir.
definitely end by 10:30. If not, maybe some delta shift to some 5-10 minutes where delta is not greater than
Can you
10
please
minutes.
also explain the topics of edges, backward edges, front edges, and cosmos?
Uh, okay, I will see. Depending upon the time I have, I would like to go in detail. I will decide whether to go in detail about that or maybe quick briefing is sufficient.
so is it better we first cover DFS and rest of the topic, and after that you can cover the doubts regarding week 10 or summaries?
Okay, I don't want to change my agenda again. See, once I fixed, I don't want to
Because
change.
it is no use for people who regularly attending the session. Like we attended the Friday morning session, and
Okay.
Yes, sir. In that till BFS, they have cleared everything.
See, that is why I'm telling you. If you discuss in this thing, maybe it would have better if you just wait for 15 to 20 minutes. Maybe I'll just increase my speed and I will discuss. See, what all is necessary, I will discuss. Okay. If I start directly at BFS, I would like to talk about the directed graph or and undirected graph, and I would like to talk about the edges between them and how VFS works in a directed graph and in undirected graph and all. So at least some basic stuff I just wanted to do. Okay. So as I said, please bear with me for the first half an hour or such. Those who are those who have attended Friday's session. Firstly, may I know is my screen visible? Because I
Yes,
cannot
sir.
see it. It's not
Yes,
working like
sir.
Gmeet. Okay, visible, right? A black screen.
Yeah, 9-1, sir.
Yes. So graph theory is in our maths one is nowhere connected to the previous 9 weeks. So graph theory is a special branch in mathematics, and it is highly widely used branch in recent times because this is the practical applications of mathematics which we see. So there are many practical applications which are directly connected to machine learning or maybe in the programming side and in many other places. Okay, so this has recently become widely popular. And what is this graph theory is basically is about? It's all about some nodes which are defined with some properties, and those nodes are connected with some edges. And how the connections and relations uh, we can show in a graph is what graph theory is basically. Okay, so I'm very much in layman, putting this all this in layman terms, because I prefer to talk in layman terms rather than uh, theoretical or proper definitions. Okay, so if you need proper definitions, you just go back, watch the lectures, and that is sufficient. I don't want to repeat the same stuff again in this session. Okay, so I'll be talking in a very simpler, easier words, and sometimes I may go wrong, and you should correct me. Okay, so we will start then. So basically, a graph. So why we are interested about graphs is because, one, if you want to understand the data or connections between two features in your data. So if I have given you a spreadsheet and some numbers, and if I have written something like this is connected to this thing is connected to that, and so if I am typing or whatever textual uh, words I have given you, it is highly difficult for you to analyze what is happening. Rather, if you have a pictorial representation of the same data. Okay, so graphs are basically a pictorial representation of the data. Okay, so this is very simpler way in which I can define a graph. Okay, so then once I define a graph, and I should tell you how the graph looks. So graphs are basically it will have some nodes called as you can label it or unlabel. So these are called, if I have given some name to that node, that is called a labeled graph. If I didn't give any label to the graph, any label to the node, it's called unlabeled graph. So these are called, we represent it like this. So these are called nodes. And so these are called nodes. And there will be one more component in my graph, which is called edges, which connect these nodes. So maybe this A is connected to B, node A is connected to node B, node B is connected to node D, node E is connected to node C. So these are some connections between these nodes. Okay, these are called edges. And in that edges, there is some classification uh, we introduced. So the classification is like direct edges and undirected. So what is this direct edges and undirected edges? Is if I have given some direction to my edge, so those edges are called directed edges. And if I didn't give any direction to my edges, then those are called undirected edges.
So what
So
do you mean by direction? Does it
yes,
mean
what,
A from B?
right? Okay, so that's a good question. What do I mean by a direction? So if I have given an edge like this, and I didn't define any direction to it, right? Like I don't know which side the edge is. And if I had said, if I had introduced this arrow kind of thing, so now I know this is a directed edge starting from here and going this side. So this is the direction that I. So what I meant is, if I have, so this is an undirected graph. So you can see I haven't given any direction to my edges, and a directed graph will look like this. So previously I have used variables to label my nodes, but now I am using numbers to label my nodes. So with this, you can make some conclusion, I guess. I can define my nodes however I can. Okay, I can label. So if I have a graph, something like this. Okay. So now this graph is called a directed graph because, so you see the edges inside this graph. So this is this complete nodes plus the edges is the graph. So this we call it as a graph G. So this G is made up of some vertices or nodes and some edges connecting these vertices. Okay, so for a graph, I have two components. One is vertices and the other is edges. So this is called a directed graph because you see in my graph, whatever the edge I drew, it has some direction. So this is an edge. For example, this is an edge from 5, node 5 to node 2. Okay, so maybe I will call vertex or node. Everything is same. Okay, so this is called this is the edge from node 5 to node 2. It's not an edge from node 2 to node 5. So this particular edge says from node 5, and this edge is going towards node 2, but it's not coming back, or it's not from 2 to 5. Whereas in the undirected graph, if there is no direction, that by implies it is bidirectional. So that means if I haven't given specifically said anything about the direction of the edge, so that implies that it can go from A to B or B to A. Okay. So even if I denote it like this, or I simply remove those things, both are equivalent. So bidirectional edge and undirected edge between two vertices is same. Okay, so never confuse about this.
Can you just repeat, sir? Did you say bidirectional and undirected are same?
So this is same as this. Okay, so if you denote it by bidirectional, or you simply remove that directions, both are same. So it's like even the undirected graph, you can treat it like this. Undirected means it's not that it can't go from A to B or B to A. It is saying that I can go from A to B or B to A. So direction doesn't matter for me. Okay, that's why it's undirected. Okay, so this is
in the directed one that you have drawn, there is a direction between 3 and 6, but 3 is not related to rest of the any of the element in this graph, nodes in this graph. Then is it still a part of this graph?
Yes.
And how searching can help? It will not be difficult for searching.
I didn't start the word called searching, right? Let's not go too far ahead, and let's not be behind also. Okay, just give me some time. I will come there.
So we have covered that. That's why I got this doubt based on the graph you have drawn.
Okay.
In my opinion, 3 must have linked with some other element. So not
okay. What do you want? You want a BFS starting from 3?
Maybe starting from 3 or from 2.
Starting from 2. Okay. So if I start from 3, your BFS graphs looks like this. That's it.
That's only.
Okay. That's it. Okay. So you can't reverse.
Sir, your voice is not.
Is that so? Is my voice not clear?
No, it's audible, sir.
Audible, sir.
Sir,
Audible,
just
sir.
wanted to ask that like in a directed graph like this one only, if we have some bidirected edges and some unidirected edges.
Correct.
So, like, will we call that graph directed or unidirected,
That's a
undirected?
very good question. So you tell me. So if I have a graph which is like this, okay, only maybe 4 vertices I take. One has a direction, and this is bidirected, and this is bidirected. This is also bidirected. Okay. Now, with your guess, what would
I
you say?
think
Is this
directed.
undirected
It
or
will
directed?
it will be directed
It will be
Directed,
directed.
sir.
Directed.
Why?
because it is one unidirected edge.
Bidirectional.
Correct. So that's how I can define. I say if I have defined it
So
properly,
bidirectional is same as so should we consider bidirectional as directed or undirected?
bidirectional.
It will
I
be
I
Bidirect-
didn't.
it will be
I
undirected.
So should bidirectional graphs be considered as directed or undirected?
So if it is completely graph is bidirectional, complete. Whatever edge you see in the graph, if it is bidirected, then it is an undirected graph. Okay. But here, if you see,
There is no specific direction, sir.
there is no.
Undirected means it can go
That's what.
anywhere. No?
That's the point. I talked that point here, right? So no direction means it says that I can go anyway. I can go from A to B or B to A. So direction is not defined. Okay. So that's the
At any
point.
point, it is means sir. Here C to D is only one direction, so it is not directed, na sir. This
It
graph
is
is we consider directed.
this graph is a directed graph. You wanted it to be
Yes, sir.
undirected.
Means sir, if there is one arrow here, C to D is only once. It's going only to the D. So
Hmm.
this graph is considered as directed, sir.
Right. So okay, maybe I will write that point. Okay. So that is directed graph. Why that is directed? Because I will write this statement. Maybe this will give you a clarity. I will first write undirected graphs definition. A graph G is called an undirected graph if every edge in G is bidirectional. So bidirectional, I mean this. Okay. So that particular every. So this every is important. So you see this. So A to
So in a
B,
graph, if even one edge is directed, it is a directed graph.
it is directed graph. So this graph which you are seeing here, this is an undirected graph.
Right.
Okay, you can simply
Because
ignore
there is no
the
any
directions.
one.
So this is
So
an
basically,
undirected graph.
we'll give preference to undirected graph. If it is a bidirected, then we'll call it undirected, not bidirected.
But why we call it? Because if every direction is bidirectional, there is no need to show the direction. So you can
Yes.
simply ignore that directions to every edge, and you can simply draw this graph very easily like this.
Okay.
Okay. I hate listening to my voice. Okay, please be on. I can listen to your voices, but I seriously hate my voice. Okay, thanks. So this is an undirected graph. So directed, what is the directed graph? If there are some edges which has only unit one direction, just like this. In this example, I have three edges which are bidirectional, but I have only there is one edge which is only unidirectional. So this edge breaks our definition of undirected graph, and it falls into direct. Okay. And every graph is either directed or undirected. Only these two possible cases are there. There is no graph which is neither directed nor undirected.
Sir,
Yes.
so all undirected graphs have bidirectional edges. Is it true, sir?
All
Bidirectional edges exist in undirected graphs. Is it true, sir?
Why do you need all these things? I don't understand. See, that's what I'm trying to make a point. It's not that important. Okay, be on these lines. What is a directed graph and what is an undirected graph? Don't get deep into those things. Whatever you said,
Sir, I
statement
have
is
a doubt.
okay. Huh.
Sir, I
Yes.
was solving the textbook questions, and there was a question that there is an undirected planar graph with 169 vertices, and there are options like how many edges does it have. So there were like 4 options, and shall I read out those options? I did not understand how do I get to the solution of that
Okay,
question.
for that you need the property of planarity.
Okay.
Property of planar graphs.
Okay.
Okay. So how does a planar graphs look? And before that, you should know, before knowing properties, you should know what is a planar graph.
Yes, sir, I know that. No edges are crossing each other.
Only edges should only intersect at the vertices.
Yes.
Right. So
Right.
for a 4.
Can you please proceed to the next topic, sir?
Yes, yes. I will. Okay. Just give me a second. Even they are my students. Okay. When someone asks a doubt, I should reply to them.
Okay, sir.
Okay. Okay. So I will just discuss that when I come to planar graphs. Okay.
Okay, sir.
Yeah.
Yes, sir. I had also doubt in that question. So after that,
We will come there. We will
yes,
come
sir.
there.
Yes.
Okay.
Yes, sir. Okay, sir.
Okay. So before moving forward, I would like to mention few terms which I'm going to use, and I sometimes interchange the terms. So I sometimes call vertices, or sometimes I will call nodes, or I simply call points. Okay. All these three are same. So all of them are same, and all of them represents these things, a circle inside some label. Okay, so these sometimes I call vertices, I call nodes or points. Everything refers to the same. Okay, and one more thing is I sometimes call edges or connections or lines. Okay. So yeah, all these three are same, all are same, and these refers to these things. Okay, always remember a graph is made up of two components. One is the set of vertices, so that set is denoted as, here it is denoted like this, so A, B, C, and another component is the set of edges, which is A, B, B, C, C. Okay, so every graph is made up of these two. So we have talked about directed, undirected. These are the two types of graphs, and now I would like to discuss these are not the only types of graphs. And if I talk about some other types of graphs like cyclic, acyclic, connected graphs, disconnected graphs, complete graphs, and previously you guys have mentioned planar graphs. So there are many types of graphs, and these types are, so we classified these graphs into these types based on if some graph is satisfying some property, so we put it into that particular type. So what are the cyclic graphs? So okay, maybe I will not discuss everything. Whatever I require, I will talk about them. And with that, you can actually define. So if you are a master of the definitions, you can give me the definitions of the other graphs also. So one thing I would like to discuss is a cyclic graph, because when I talk about DAGs, I need this acyclic graphs. So acyclic graph means a graph that does not contains a cycle. Okay. Now I introduce a term called cycle. So what is a cycle? Right? So this is a very common question you should get. So what is a cycle? A cycle, maybe I will write it in very simple terms. A cycle is this. So you start from a vertex in a graph. So you start from some vertex u. So I don't want to specifically pick anything. If I start from a vertex u in a graph, and if you can able to reach back to you by traveling along some edges and vertices. So as I said previously, why graph theory is important is because I have written this thing. Okay, you start from u in a graph. If you can able to reach this and this, traveling some edges, that's called a cycle. And this looks, for understanding purposes, this might be a bit trickier, but I will show you graphically what this means. So I have a graph like this. So u0, u1, u2, u3, u4. Okay. So I have 5 vertices. Okay, and some edges connecting these vertices. Now what this cycle means is, if you start from u or any you just start from this. Okay, so you are here. So if I am here and I have an edge here, so that means I can walk on this edge and reach here. So like this. So this is what traveling means. So I am at the vertex u0, and I took this edge u0 to u1. So treat it like you are in the city Hyderabad. Okay, and you have took a road that connects to Mumbai. And if there is a road that connects to Mumbai, you took that road to Mumbai, and from Mumbai to Bangalore, Bangalore to Chennai, Chennai. And if there is a road back to Chennai, back to Hyderabad, then you made a cycle, right? You started from one place and you traveled along some road, some cities, and you came back to the same city where you started. So now tell me, is if I start from u0, can I come back to u0?
No, sir.
By traveling to some...
No, sir.
No, sir, we cannot.
No,
Yes.
right? So I
We
can
cannot.
go here, and from here I can go to u2, I can go through u3, I can go to u4, but I can't come back to u0. So u0 is not a right pick. And like this,
U0, U1, U2, U3, and then again to U0. So can we call that a cycle?
which
Like if
one?
there's a
u0,
connection with U3 and U, like from
u0,
U0 to U1, U1 to U2, U2 to the U3, and if there is a connection from U3 to U0, then can we call it a cycle?
if there is a connection, then we can call. But right now there is no connection. Okay.
U1
So,
is the connection where we can come back, sir, if you
right,
start.
right, correct. So if I start from u1, I will show you a simple cycle. So if I start from u1 and I traveled along this path, so I can travel because there is an edge going from u1 to u3, and I can reach here u3. Once after reaching u3, I can see some edge that is going to u4, and I can come here, and from u4 I am able to see one more edge that is going back to u1. So I started from here and I came back to u1. So what that tells is, I started from u1 and I went to u3, and from u3 to u4, from u1 back to, from u4 back to u1. So this forms a cycle. You can see some sort of cycle, right? Or maybe
So we can also go U1, U2, U3, U4, and then
that is also one more possible way. That's a good observation. You see this? You see this cycle? There is some cycle.
So, sir, can we say that if the edges behave like a loop, then it is a then we can reach out to from where we.
Okay, let me. I should have told this at the start. So we are only considering simple graphs. Simple graphs meaning there are no loops like this. So this, in our particular course, we are not going to use those edges. Okay, so this is not allowed. So we no need to talk about that. Okay.
Excuse me, sir.
On this,
Sir, is this only for directed graphs? Sorry, yeah, directed graphs or both for directed and undirected graphs?
Not necessarily directed. So I can give
Okay,
you a
sir.
small example which can work for undirected also. Okay. So here you can see I can go from A to B, B to A to B, B to D, D to A. Right? So that means D to A. So I can come back and I can form a cycle. Okay. So
Yes.
what acyclic means is I should not contain cycles like this in my graph. Okay. So that's what acyclic graph means. If in a graph I don't see any cycles I mean like this. So
It's no
starting from one
if
point.
not a cyclic graph, it can be said it's a cyclic graph.
So
A
overall,
graph
this
which
is
is
cyclic
not
graph, right?
cyclic.
See, if you had born some 500 years ago, then you would have said non-cyclic. We would have defined it as non-cyclic. But the term is already defined and it is said acyclic. Okay. So if you want to interpret it in that way, you can.
Sir, so can we understand, like to understand, can we say there is no cycle?
Yeah. Yeah.
This whole graph will always cycle or only this part? This whole graph will be called cycle or this part U1, U3, U4 will be called cycle?
This U1, U3, U4 is called a cycle. This
So we can call it as overall as a cyclic.
Not a cyclic graph.
So this
No,
is a
sir.
cyclic graph, right?
What he wants to ask is like if this whole graph will be called a cyclic graph on only that particular part.
I didn't define what is cyclic, right? Okay. If you are master of the definitions, can you give me how do I define cyclic? Maybe common way to say is which are not acyclic, right? That's what we say, but graph theory doesn't say that. Cyclic graphs are graphs.
You start from one vertex, one node, then you reach by edges to that point only in the end, then it is called a cyclic graph,
You
like
start.
that. If you start from one node, one vertices, and travel through edges and reach at that point only, then it can be
We
called a
can
cyclic
repeat
graph.
it, sir. The repetitions.
See, these are called cyclic graphs. Okay. So the cyclic graphs are the graphs in which if I start from any node, I can come back to the same. Okay. And these are for a 3 vertices. This is how cyclic graph looks for a 4 vertices. This is what cyclic graph means for 5 vertices. This is cyclic graph. So these are called cyclic graphs. And okay, we don't need cyclic graphs that much, and these are not widely used. Acyclic graphs are widely used and it has many applications. in practical scenarios, real life scenarios. So acyclic graphs are more important to understand.
And just wanted to ask that the graph which you mentioned here, the U1, U0, will it be called cyclic graph or acyclic graph? Like it has only two cycles and others are not in a cycle. So it will be called a
Okay.
cyclic graph.
It is not called as a cyclic graph. It's called as a, we just call it not an acyclic graph.
Okay, but it won't be a cyclic graph also.
It will not be a cyclic graph. Cyclic graphs are like this.
Okay. Okay.
Okay.
So then what we call it, sir?
Not
If it is
an
not
acyclic
acyclic
graph.
and cyclic, not a cyclic.
Not an acyclic graph. That's it. We didn't define. See, because there are n numerous number of graphs like that, and they don't have. If you find any cycle inside graph, and you no longer use it in the practical purposes. Okay, so that's why we didn't name it, and we don't want it to be named. Okay. Yeah. So with that, we will move forward and talk about this complete graph a little bit, which I want this to be used later also, I hope. If not also, it's an important graph to be noted. And when do I call a graph complete?
When every vertex is connected to every other vertex.
Right. If every pair of vertices are connected by an edge. Now, take a minute and think, will there be any directed graph which is a complete graph?
Yes, sir, it can be, no?
It can be.
Like if it's a cyclic graph and then there are connections in between, sir.
Every pair of vertices are connected by an edge, direct edge. It's not path. So if I see any two vertices, the first
Can
vertex
you give
to
an
be connected.
example, sir? Then we can find out.
Okay. So by an edge. It is called a complete. Can someone please be on mute? So an example is this. So if I have, let me say, 4 vertices. Okay, I have 4 vertices. Now what I defined is, you pick any 2 vertices, and those 2 vertices need to be connected by an edge. Okay, so if I pick A and D, so A should be connected to D and D should also be connected to A. Okay, something like this. Similarly, any two means BC, AC, AB, BD, CD. So this is a complete graph and it is denoted as K4. Complete graph with 4 vertices. Okay. And how many number of edges are there in this?
6 edges.
6.
6. Now a question which I'm going to ask now, and I want everyone to try this out. Find the number of edges.
This is a directed or undirected graph.
See, did I draw any directions to that?
No.
Then what is the graph?
Undirected.
That's it. That's it. See, these are key observations you should make always. See, when I am writing anything or when I'm drawing like this, if you see any directions to the graph, then that is directed. As simple as that. If I didn't draw any directions to the graph to the edges, it's an undirected graph. Okay. Yeah.
Is it also clean?
Is it also
a clip?
Where did you?
Sir, in CT we read that.
Okay, in CT. See, clicks are subgraphs of a big graph. So if I had something like E like this, okay. So this is a bigger graph, and in this big graph there exists a click. This is a click. Okay. So click is slightly different from complete. So all clicks are complete graphs. Yeah. And yeah, people don't know about click, forget. As of now, no need. What is the answer for this?
10,
Right down.
8,
9.
10, sir. 10.
10.
8.
8 or 10?
10.
10, sir. 1 by 2, n into n minus 1 is the formula for edges in a complete graph.
Okay. So you can use the formula, you know, or you simply take 5 vertices, join everything. So I drew already 5 edges like this. So 6, 7, 8, 9, 10. A star with some cycle outside. Okay.
Sir.
So number of edges are 10. Yes.
It's always double, na, sir. You can remember.
What was
No,
the
it's not
formula, sir?
always double, right? So now I'm going to that formula. Yes, I'm going to that formula only. See, for 4 vertices we have 6. For 5 vertices we have 10.
Sir.
Hmm. Okay. So if n is 4, I have the total number of edges is 6, and is 5, the total number of edges is 10. So what does this mean is basically complete graph, any two, if I choose any 2 vertices, there is an edge. So how do I choose 2 vertices out of n vertices? If I have n vertices, how many ways I can choose 2 vertices? People who know combinations, it's simply NC2.
NC2.
And the expansion of that NC2 is, even though if you don't
N
know,
into n minus 1 by 2.
n into n minus 1 by 2.
So can you say for which one there's NC2, sir? For which question?
Which question? A complete graph with n vertices has n into n minus 1 by 2 edges. So do I need to write all of them? I don't think so. See, some things you should do. Okay. So let me move forward on this. So yeah. So I will also want to discuss this planar graphs. So planar graphs require some more intuition about how you draw the graph and everything. So how do I define planar graphs is in this way. And again, this is not a proper technical definition given in the textbooks or somewhere. So it's my words. Okay, simple words. So planar graphs in a graph G, any 2 edges will meet or intersect at vertices only. Okay. Again, I will draw the graph of this and then I will explain again. Okay. So then G is planar. Oh, okay. In a graph G, or if I can, okay, sorry. So if I can draw the graph G such that, so this S dot T is such that, okay, don't ask me what is that S dot T. That is such that any 2 edges will meet or intersect at vertices only. What this means is, so you see this now. So I will take K4 only. So previously I have drawn a complete graph with 4 vertices like this. Now you see, if I pick these two edges, this edge A to C and B to D. So these two edges are meeting in between, which is not a vertex at all. Okay. So this is a meeting point. Meeting point for AC, BD. Okay. So these two edges, which I am referring to, so this edge and this edge, these two are meeting at this point, which is not a vertex. Okay. So the other way of defining planar graphs is, if any two edges are intersecting or meeting, they have to meet at a vertex point. Okay, but here it is not meeting. Can I say this is a non-planar graph?
Right, sir. You can say it is a non-planar graph.
So as of now I can say, but I also said, if I can draw the graph G. Okay, so instead of drawing the graph like this, if I had drawn the graph like this, so the same graph, right? Instead of drawing AC from inside, I just connected AC from outside. Now if you see, none of the edges are intersecting in between. So all the edges which you are seeing on the screen on the right side, if at all edges are meeting or intersecting, they are meeting at this vertex A. These three edges are meeting at this. These three edges are meeting at D. These these three edges are meeting at B, and these three edges are meeting at C. Okay. So if you are able to draw the graph in such a way that no two edges are intersecting in between, such graphs are called planar graphs. So this is not the way I should draw. This is the way I should draw, and this is a planar graph. Okay. So similarly, I can show you many planar graphs. So this is a planar graph. So none of the edges are intersecting in between. Okay. So this is a planar graph, and I can extend this planar graph however I want. Like this. So there are big graphs which are planar, and also there are graphs which are not planar. So now not planar graphs looks like this. So if I take pretty simple not planar graph is K5. K5 is not planar. You can check. People who have notebooks with you, try drawing the complete graph. So this is complete graph with 5 vertices.
So the edges should meet only at the vertices. There
Right.
can't be any intersection.
So people able to draw. So now see these 5 edges, they are not intersecting. Let me slowly draw one more edge. So let me draw this edge. A. So even now also it's fine. Similarly, I can draw A, D.
A to D also.
Even now this looks like a planar. Now I have to connect BC. So if I go like this, it will intersect. So I shouldn't go like this.
Sorry, go from A side.
Go from A side. Okay. Now I should also connect B to D and E to C. So still remaining are BD and EC. So which one shall we connect? BD or EC?
Sir, so in a complete graph, every vertices must be connected, sir.
Yes, that's the definition of complete graph. Still I have to draw. BD and EC are left still to be joined. Okay, so
Only
I
one
can
of them
join
can measure.
BD. I can draw BD also.
You're
No
drawing a
worries.
complete and
I didn't understand. Hello.
Sir, why not do AB, BE, ED, DC, and AC in this
AB,
case?
AB.
Sir, why not connect AB?
AB is already connected, right?
So what about an interior connection of BD? Not
BD.
externally, but
See, if I connect internally, this will
Yes,
meet,
sir.
right? This will intersect in between, right? And which makes it non-planar.
So only
So
C and D is equal to connect.
Now still C and E is still to connect, but if I go from inside, that will intersect here. If I go from outside, that will intersect here. If I do this path also, this side also, that will intersect here. And any different possible ways, if I try, that there will always be an intersection between two edges in between. Okay, so this is not a planar graph. Okay.
But this had this graph got a 2D structure, then we could have connected them.
Okay, so that's what planar graph mean. So the word plane, planar, you should be able to draw that in a plane, on a plane. So now on screen. Okay, so if you are not able to draw, then you need that 2D, 3D. In 3D, I can definitely draw. Okay, without intersecting. But on plane, if I can able to draw my graph without intersecting two edges in between, then those graphs are called planar graphs. And if I am not able to draw, so here I am not able to draw. However, way I wanted to connect E and C, in every possible case, I am intersecting in between, and I can't draw. No, so I can't draw the complete graph with 5 vertices on a plane such that any two edges intersects only at vertices, satisfying that condition. So I can't do that. Therefore, it's not a planar graph. Okay. So that's about planar graph. And with that, I will just move to next important topic, which is called.
Sir, I had a doubt in this topic, sir.
Scroll up
Planar
for a minute.
graphs.
Can you please scroll up for a minute?
Hello, sir.
So,
Yes,
sir,
yes,
because C to E is not possible, it's not a planar graph, sir.
yes.
Okay.
Sir, I asked a doubt before on a number of edges in an undirected planar graph of having
Yes.
169 vertices.
Hmm.
So how do we solve that, sir? In the textbook also there was no kind of solution. The answer was directly given.
Okay. So you tell me this thing. I have given you 5 vertices, right? Here.
Yes, sir.
So how many maximum edges I can draw such that the planarity holds? 10. Complete
1,
graph
2,
has
3,
10
4, 5,
edges.
8,
6.
sir. Sir, 8.
8, sir.
8.
8, sir.
Okay, can you count again?
7,
All
8,
the white
9,
edges.
9, 9, 9.
9. Right? For a 5 vertices, I can have 9 edges. Right?
Okay.
At max 9 edges. If it is going beyond 9, that definitely can't be planar. Right?
Yes, sir.
And there is a direct formula, and I don't want to prove that formula right now because it requires some knowledge on phases regions and all.
Yeah,
So
yes, sir. I heard like R is equal to vertices is equal to edge plus faces plus two something, sir.
right. So it is bounded inside. So
Hmm.
just check that, okay? You just go online and just check the
But
formula of it.
in the question, there was no mention of faces. There were just vertices, and they asked for edges. So
So it was, how many
I was
vertices are
confused.
given?
169 vertices was given, and they just directly asked edges. There was no mention of faces. That's why I was stuck.
Okay, so they were talking about edges, number
Yes,
of
sir. Just the
edges.
edges. Yes, sir.
And can you give me the options?
Options. Yes, sir. Uh,
Okay.
Number of edges will be less than 14196, 14,196. This is the first option.
Hmm.
Second option, edges will be less than 14,281. Third option is edges will be less than 169. And fourth option, edges will be less than 28,382.
Okay. So I don't think this requires that boundedness. This is sufficient. See, a complete graph with 5 vertices itself is not a planar.
Yes, sir.
Correct? Agreed?
Yes, sir.
How many edges will a complete graph with 169
So,
vertices
but
will be?
here they already mentioned that it is a planar graph, the question.
Yes, I agree. For
Okay.
that, how many edges is possible for vertices? How many for a graph having 169 vertices?
169 into 168 by 2.
Which is 84 and 16984.
Where it is coming 14196.
14196.
Okay.
Okay. So what it says is basically, if definitely you know that if it is a complete graph, it won't be planar. If it is given planar, definitely the number of edges should be less than 14196.
Yes, sir.
Right? Yeah. So that's it.
Yeah. Got it, sir. Thank you, sir.
Okay. So let's move and discuss the most important topics which are going to be the key takeaways from this particular week and in your future also.
Sir, just a small question from that planar graph. So, if planar, if some vertices are given, so will there be the same formula like that NC2 or anything like
No.
that?
See, that requires some more knowledge. As like just now I said, right? That requires some more information about these phases and all, which professor also don't want to get involved, and even we don't want that. Okay. So you won't go beyond 8-9 vertices. Okay. So this 8-9 vertices are very small graphs compared to your programming and ML problems which you're going to see. So in ML, at least some data you are going to see is 10,000 cross some 300 or 400, which is very big data. Okay. So getting some connections
Sir,
among
another
them.
small doubt, sir, regarding the planar graphs. I don't know, please correct me. The thing I have got to know is that in a planar graph, for coloring, maximum we can, it is just 4. So if I have planar graph, then the maximum number of colors that I need for coloring the whole graph is 4. Is that
4.
correct?
Correct.
Okay.
That's called 4 coloring theorem, and which is again widely popular theorem. And
Okay,
one
sir.
practical application of it is, you know, the world map, right?
Yes, sir. Yes, sir.
So none of the city shares boundaries with more than 4 or something like that.
Yes, sir.
Okay. So you know that that connects there. I will come to there, but before that, as I said, the most important topic and which is going to be useful in future in coding or in ML, which is called reachability. Reachability of a graph, which is very simple stuff, but yet quite a bit popular. Okay. So in graph theory, basically, reachability refers to finding a path to reach from one vertex to another vertex. Again, this is more or less looks like a proper definition, but it's not. So what I said is reachability refers to find a path to reach from one vertex u, maybe I will give u, to another vertex v. Now this is how we use reachability word term. If there is a path, so if there is such path, if there is a path from u to v, then we say then u is, so v is reachable from u. So in very simple terms, so you are at one position u, and if you are able to go to v, then obviously what it says, what it tells you, I can actually reach from u to v. And in other words, I can the destination part v, for point v, is reachable from v. That's it. That's what reachability means. And if there is no path, there is no path existing, or if there is no path from u to v, then v is not reachable from v. Okay, so that is what reachability means. For example, so for suppose this is
Reachable or not reachable is depending based on the word edges only. Like already
based on
existing
the
edges.
path. Okay, so let me draw something. So view this. This is D, somewhere E, and somewhere this is connected. Let's connect this. Let's connect this. Okay. So now this is a graph. My first question: is this graph undirected or a directed?
Directed.
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 Good. How many vertices are there in this graph?
Six.
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 Very good. Now the next question: is F reachable from D? Array, please be on mute. Or please stop the YouTube thing all which is running behind you. Maybe you should stop that when you are unmuting yourself. Okay. Okay. So now my slightly difficult question is F reachable from D?
Yes, sir.
Yes, sir.
Yes.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes,
Yes.
So what should I check to answer this?
There
Yes,
is
sir.
a
Check if there's
edge
a
from
path
D to
from
F.
D.
Path.
A to C, C to A to B, B to F.
So what we should check is, we should check, is there a path from D to F? That's it. So this is what I have to check. And how do I check? So I'm at D. Now from D I can go to C. From C I can go to A. From A I can go to B. From B I can go to F. Yes. So starting from D, there is a path from D to F. So the path is this: D to C, C to A to B, B to F.
So,
Right?
so I'm able to understand all this, but then when it comes to application questions, or even when the
I will
letters are,
take that example also. I will take that example also.
yes, sir. So like
Yes,
even
I
the
will take.
first question of the activity 10.1 first question I was not able to do.
Okay, maybe I will take that also. Okay.
Sir, sir,
So,
sir. Is the length of a path as a constraint for reachability?
no, definitely not. See, we are only talking about, can I able to go from this vertex
So
to
is
that
the
vertex?
direction a constraint?
Of course,
To
direction
reach
is a constraint. So I can't go to D to E, right? If there is no road connecting Delhi and Hyderabad, how can I go from Hyderabad to Delhi through road? Maybe I can go from some other ways. If there is no path at all, how can I go? I can't go. Right? So yes. So if the question is like this, it's very, very easy. Let me complicate the question slightly. Find all the vertices that are reachable from C. Now my question is slightly different from the previous question. So what I want here is, it's not yes or no. It's not binary question here. Previous question was yes or no. But here I want all the vertices that are reachable from C. So now this is the graph.
ADBF.
ABF and D. ADB.
DABF.
E
Sir,
is not
DABF.
reachable.
DABF.
DABF.
I hear most of you saying DABF or except E.
Yes.
Can I say like that?
Yes, sir.
ED, sir.
Right? Except E. So I can, yes, maybe I am at C. Now my question is, where all I can go? So I can go to D, I can go to A, I can go to B, I can go to F. Right? So the answer to this question will be somewhat like this. So I needed find the all the vertices. So it's like set of all the vertices possible. So A, B, D, F. Correct?
So we can reach E also, no?
How can you reach E?
C to D and E.
C to
At,
D. And can I go from D to
no.
E?
No, sir. Right.
No, sir.
No, right? So there is no, it's not a bidirectional. It's only, I
Okay,
can
okay.
only come from E to D. Now let me complicate the question slightly. Now my question is, find the vertex from which every other vertex is reachable. Okay. So what am I asking? Find the vertex. So given the graph, you should find the vertex from which I should start so that I will reach every other vertex. So
Sir, E.
can you able to see any vertex, such vertex in this graph?
Yes,
It
sir.
is E, sir.
E, sir.
E.
It's
Very
only
good.
E.
Those who have said E, yes, you are correct. So you see what the question is, not about is it reachable from this vertex to that vertex, or is it not, I need all the vertices which are when I am at a position and which all places I can go. But this question is slightly different, wherein it asks, where should I stand such that I can be able to reach to every other vertex. So we saw C, from C I cannot reach E, from D also I cannot reach E. So C, D can be removed. A also cannot reach E, B also cannot reach E, from F also I cannot reach E. So if I start from E, what happens? I can go to B. Yes, I can. Okay. So using this, I can come to D. So if I can go to B, from B to F, I can go. If I can go to D, from D, I can go to C. If I can go to C, from C, I can go to A. That means if I started from E, I can reach every other method. So answer will be. So you observe this. I have given you the graph, and from the graph, you directly ask a straight and slightly trickier question, and wherein we include these questions as straightforward questions. Okay. So if some real life scenario is added to this, some situation has been thrown into this. Like for suppose, if I say there are some cities in this in India, mainly some Delhi, Mumbai, Chennai, Agra, or like that, and each of the city has an airport, and also some cities has a direct flight, and some cities does not have a direct flight. Okay, and a graph representing that particular data is shown like maybe this, like this. So, okay, so the same graph, but instead of giving graph, we might give you from Agra. There are direct flights available to Chennai, Delhi, and Mumbai. And from Delhi, there are direct flights available from Agra, Bhopal, something like that. So I was trying to think for letters. So what can I give for A, B? So that's why I'm using those cities. So like this. So if I had included uh, context into this, and I say now you draw a graph where each vertex represents a city, and a directed edge from vertex I to vertex J if there is a direct flight from city I to city J. So like this we can give. And now how the questions might be? Any guesses? If you are an instructor to a course and if you are dealing graph theory, what questions you are interested to ask? Anyone?
So
Okay,
could you repeat
path.
your question?
So I said now I am involving some context. So this is the context. There are some cities. Maybe I say for D I will say Delhi. For C I will say Chennai. For A Agra is sufficient. B Bhopal. Okay. So for G maybe Gaya. For E Ernakulam. Okay. So these are the 6 cities I have given, and I said the context is like this. So there are, okay, maybe like this. So each vertex represents a city, and each edge, direct edge from vertex I to vertex J represents a direct flight from city I to city J. Okay. So this is the scenario now. So use the same graph. Now if you are a master of creating questions, so how would your first question will be? Maybe you can relate the previous questions. So the direct questions you just combine with the context. How will your questions be?
So, what is the shortest path from Delhi
Shortest
to
path. Okay, I did.
Delhi
Okay,
to Bhopal?
okay,
Or
that's okay.
and question number two can be like this: that Delhi, as it is a capital, so I want Delhi to be placed there, from where I can reach everywhere.
So that's a valid question. So if I am at Delhi, from Delhi, what all cities?
Have you drawn the graph yet, sir?
So I said take the same graph.
Okay, sir.
So that's why I took D, C, A, B, C, D, E, G. Why I took G? F, right? Which city starts with that?
Faridabad.
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 Oh, Faridabad. Okay. So A, B, C, D, E, F. Okay. So take the same graph, and it's not about the graph. It's about, see, you should always understand how a question can be framed. Then only you can able to solve that particular question. Okay. So previously, what are the questions I raised? So the very first question I asked is F reachable from D? Okay. So if I have to ask the same question involving context, how should I ask?
Can a person traveling from Faridabad, go travel to use a direct flight? Or you can actually ask this like true and false questions, like multiple select questions, which among the following are true, and you can give a lot of scenarios and
correct,
select the correct answer.
So that's how the questions are something like this. So what all cities can I travel? So this is one way of which we can ask. Another way is there a way? So the very first simple, is there a way? I just need, is there a way to reach from Delhi? So from one vertex to Faridabad via airways, via these connections. Okay. So what's the difference between this and the previously asked question? I asked like, is F reachable from D? And is F reachable from D? And is there a way to reach from Delhi to Faridabad via airways? What's the only difference? Can someone point out?
In the first case, we are looking for all the edges that are connected to the node D.
Not this. So previously a direct question is I have asked, right? Is F reachable from D, from vertex D?
Delhi to Faridabad, same questions only, but here it is more
context involved. That's it, right? So you should be able to break down that context into the mathematical terms or mathematical words. So just like what they are asking. So they are simply asking, they given a graph, there are some connections, and they wanted the connections, they are defined it as, so connections I mean edges. Edges I defined, they are defining it as, if there is a direct flight, then I have to draw a direct edge. So that's how they define the connections. And if you draw the graph, for example, let's say it looks like this. Now what they are asking, they are just simply asking, from Delhi, can I reach to Faridabad? Okay. So that's what. So it is same as asking, is F reachable from D? Right now D is replaced with Delhi, F is replaced with Faridabad, and reachability is replaced with way to reach. That's it. And similarly this and the above one has a connection. So find all the vertices that are reachable from C is same as asking, you are at Delhi or from Delhi, what all cities can I travel? So if there are some connections to those cities, then I can travel to those cities. So something like this. Okay. So the context and the normal straightforward questions, the only difference between them is how you should learn how to break down that context and then solve the problem. Okay, so let me move forward, stating that. And next I wanted to talk about vertex coloring. Okay. So,
for this, can you discuss the activity question?
Okay, maybe I will. Can I discuss it at the end? I'm running out of time, so I just have to quickly jump to the main topic.
Yes, sir.
Okay.
So the problem is when the application of these comes, sir, these topics are actually fine.
So are you going to talk about applications of BSF?
Yes, I will talk. Yes. So let me quickly move from vertex coloring. So this is just a puzzle kind of thing. See, this vertex coloring is not a concept, and you don't have to scratch your brain too much. Okay, so what you have to do is, or what you have to play in this particular game is, you just have to color the vertices such that no two vertices that are connected by an edge gets the same color. So what I mean is, if the edges are connected like this, now what you have to do is, the only thing you have to do is, you have some bunch of colors with you, and you have to color each and every vertex with some color, one single color. So for example, if I start coloring A, and I say my first color is blue, and I colored the vertex A with blue. So what I have to do is, once I colored A with blue, and A is connected to C, A is connected to E, A is connected to D, A is connected to B. So if I give any vertex the same color, like if I have given D to blue color, then what happens is, this particular edge connecting A and D, there is a direct connection, and those two vertices have the same color, which I don't want. So that means I can't color D with blue. So once I can't color any vertex with blue, I have to move to the next color, which you can take it red or anything, then start coloring. So next I move to some uh, random point, random vertex, and then start coloring, giving the next color. So this is colored with red. So now once this is colored with red, I can't color E with red because there is a direct connection, but I can color D with red because C is not connected to D. So I can have red color for C as well as D. So once I have red color for D, I can't have red color to B because they are connected. So I can't color B with blue because of this edge.
This can't have the same color.
Huh. So B cannot take blue as well as B cannot take red. So next is some new color, the third color, which is green. And I can color green to both B and E. This is as simple as that. And why this is important? So it looks like a game, but why many people are behind this vertex coloring? And again, vertex coloring also has many applications. One quick application is, maybe I can give you many real scenarios. One simple scenario which is
Political.
funnier side also, maybe I will take that. Let's suppose say there are some people, some 7-8 people. Okay, so 7 people are there, and within that 7 people, some start quarreling or some start fighting when they see each other. Okay, so you have a bunch of people with you, but there is, that if two people come across, they will definitely start fighting, they will start abusing themselves, and they will start fighting each other. And now what you want is, that what you can do is, you can draw a graph by representing those peoples as vertices, and you draw an edge between two vertices such that that edge represents the two people. So if I draw a vertex from vertex I to vertex j, that represents that the person I starts quarreling with person j. So this is how it is. Okay. So the graph, you can draw the graph. So that this person quarrels with this person. So you just have an direct edges. So maybe I will just show you. So let me take. So these are some persons. Okay, so some random 1 2 3 4 5 6 7 8 people. So maybe I'll label 1 2 3 4 5 6 7 8. So these are the 8 people. You have invited them to your home, let's say, and for a party, and that person 1 quarrels with 2, person 1 quarrels with 4, and this guy quarrels with 6. Likewise, you know that 2 quarrels with 3, 2 with 5, 2 fights with 8, 2 fights with 4, and 2 fights with 6. So this guy is quite a messy. So he fights with everyone, whoever this is. Okay, now something like this. Something like this. See, you know this. Something like this. If you have a graph with you. Now, the first thing what you will try to do. So you have invited all the 8 people to your home, and fighting shouldn't happen at your home, right? You should take care of that. So for that, what you will start doing? So maybe you have a multiple number of rooms.
Put them in
I'll
different
filter
different.
them.
So you have multiple number of rooms, and once the person 1 visits to your home, you keep him in one separate room, where person 2, person 4, person 6, you will not let person 2, person 4, person 6 go into that room. Correct? Something sort of like that you will do, right? So you will separate. You will try to keep them separately. Now, the very general question is, if you have 8 rooms, you can keep each and every one. You can give 8 rooms. But sadly, we don't have 8 rooms in our home. But how many minimum rooms you should have so that the quarreling will not happen? Okay, so that's a problem where in which you can pitch in this vertex coloring. So you can color this particular graph and see after coloring, just see how many colors you have used to color this particular graph, and that number of colors will give you how many rooms you wanted. At least that gives you the minimum number of rooms you need to separate these people. So you see this 2, 3, 5. So 2 quarrels with 5 and 2 quarrels with 3, 3 quarrels with 5 too. It's like a cycle. So all these 3 people should be in 3 different rooms. So definitely you definitely require 3 rooms, wherein you keep 2, 3, 5 separately. Correct? So like this, if you do the vertex coloring to this, then you will get the minimum number of rooms. So this is one small example. That's it.
Sir, in case of planar, we have like the conjecture, right, sir, the 4-color theorem. For non-planar graph like this, do we have anything similar to that, or is
No.
it just manual labor work?
No, manual labor work. And see, this, let me tell you one thing, this vertex coloring is not straight away. You can't see here the graph is only 8 vertices or even 15 vertices, also a small graph. Okay. Think about the graphs which have vertices of 100, 200, 300 vertices, and there is some messy connections between those vertices. So those kind of graphs, even machines take a lot of time to give you the vertex color. Okay.
Yes, sir. Is there any algorithm that does this coloring, or is it brute force?
I don't. As of now, I didn't encounter any such algorithm to my knowledge. We have to do manually.
Sir, you have mentioned something like that 4-coloring theorem. 4-color theorem.
That's not necessary as of now. You don't worry about it. Okay.
So if you would like to answer this vertex coloring, then maybe it is 7, sir. Is that
which one?
Yeah, this one, sir. 7 different color.
So you say the answer is 7, huh? I don't
Sir.
think it is 7. Can someone done this? So 2 once 2 is given, I can do this. Yeah. And then comes blue, yeah, that's it. And then I can color this with the green, this with green. Only 3 colors is sufficient, right? Minimum colors. See, that's what I said. I can color this with 8 colors also. give each and every vertex different color. That is also a possibility. But I want the minimum coloring. Minimum colors I should use.
Sir, the 5 can't be colored green.
5 can't be colored green. Why?
No. Sorry, sir.
Okay. Yeah, that's 3. With 3 colors I can color. See, with minimum 3 colors are required. Okay. So it's minimum. That's it. You can use 4 colors, 5 colors, 6 colors, 7 colors, all 8 different colors for each and every vertex. That's also an coloring. But it's not the minimum coloring. Okay. And we are interested to find the minimum coloring, and vertex coloring also represents the same thing. How many minimum colors you should require to color the graph.
Sir, is there any formula for it, or we have to see
No,
the
no.
graph and sketch it?
No. See the graph and sketch it. That's what we discussed. There is no direct formula or any algorithm.
It is a
Sir,
little
can you
bit
once
tricky,
scroll
no,
up,
sir?
sir? I think five is miscolored maybe. Sir, 2 is connected to 5 and 4, no, sir? So
2, see, there is no direct connection, right?
okay.
You should only worry about the direct connection. In that case, this is a connected graph, and every vertex is connected to every other vertex. I can.
It is a little bit tricky, no,
Got
sir.
it, sir.
I
Got it.
was doing it from the vertex 2 and noticing that lots of edges are connected to the 2.
Let me tell you one thing. See, even if that's what I said. Even graphs with 15 or more than less than 15 are treated as simple graphs, and they can be by repeated trials. You can find the minimum coloring. It's a bit manual work, but you have to do it.
Sir, why not 5 in blue, sir? Because that is not connected to 1, right?
3 is blue, right? Okay. So that is, it needs some practice. You just practice it thoroughly, and
So how do
you
we
can.
select the starting one? Like which one? There are 8 of them. How did you select 2 as the first one? You
See,
started with 2, right?
you can start randomly. In 99.99 cases, you can start randomly. Or if you want some metrics to be given to you, you just start with the vertex which is connected to most of the edges.
Okay.
Color that first. Okay.
Because
So
if we
but
start
that is
with
not.
something different, wouldn't it change the answer?
It will not change the answer. But I may color 2 with some second color, and you may color 2 with some third color or such, and maybe some interchange of the colors. That's it.
Yes.
But you will get you will color with 3 colors. 3 colors are sufficient to color this graph.
Yes,
And
sir.
no matter where you start, you can color with 3 colors. Okay.
So if the data is very big, like 50 or 100, then it would be very
That's
difficult.
what I said. Even computer takes lots of. Computer goes like iterative methods. It will start from one point, one vertex, and try to find the vertex coloring. And sometimes that 0.01 cases, what happens is there will be some noise or something would have gone wrong, and that vertex is not a proper vertex to choose, and it goes to the next vertex. So there is no proper algorithm. That is what I said. I can't give you these are the steps you should follow and you will reach the answer. There is no such algorithm written for vertex color.
Yes.
There is a question in 10.2 2 and 3. Actually, there is an overlapping of times between the games. How many minimum computers required to play?
That's a very good question to be practiced. Is there any doubt in that?
No, sir, I got. We can use this vertex coloring there
Right.
also. No?
Right. So it requires that vertex coloring. This scheduling. So scheduling is also one proper application for vertex coloring. See, if you are running a school and you have to arrange you have some 6 teachers, and there are some 10 subjects, and 10 subjects to be slotted in 8. So on a day, you assume that There are only 8 slots available and you have to run different courses throughout the week. So scheduling, timetable preparations. So there should not be any overlap between the courses which was taught by the same teacher, because he can't teach in 2 different classes at the same time. So that overlapping shouldn't be there. And there they use this vertex coloring. And using this vertex coloring, they will schedule. So there are many applications. That's what I said. See, vertex coloring looks simple. It's like a game or some puzzle kind of solving thing, but it has many practical applications. And yeah, so let's put a full stop at to vertex coloring, and let's discuss this directed acyclic graphs, which are in short called as DAGs. Okay. So from the name itself, you can define, if you are a master of definitions. Can anyone define what are these directed acyclic graphs? So you know what are acyclic graphs and what are directed graphs. Now define what are directed acyclic graphs.
Acyclic graphs
Graphs
with
which are
direction.
directed.
Graphs which are
Graphs which
directed
are and acyclic.
acyclic. Very good. That's a proper definition. So a directed graph with no cycles is called a DAG. That's it. The graph should be directed graph first of all, and it should not have any cycles inside it. Okay, as simple as that. So let me give you 2 examples. You tell me which one is DAG and which one is not.
So right side one is directed acyclic graph, I guess.
Okay, let me give Z1. This is the graph G1 and this is Z2. So which one of the following graphs is a directed acyclic graph?
G2.
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 G2. Why not Z1?
Because ACD
Because
is a
There's a
cycle.
cycle ABC,
ABCD cycle.
that
So
is
I
a cycle.
can show you many
D, E,
cycles.
B, C.
A, C, D, A is a cycle. A
A,
simple
B,
small
C,
cycle.
D, A is
Yeah.
also a cycle.
A, B, C, D,
From
again
everywhere
from
it is
D.
cycles, sir.
Uh,
From every
so
point. D,
it's a cycle.
A,
You
B,
start
C,
from
D.
B, C, D, A, B, C, D, A, C, and C, D, A, B, C. So
Everywhere.
there are many cycles inside it. Even though you get one cycle is sufficient to tell that it's not an acyclic graph. Okay. So now, why this is that?
So
Because
even
we
in
cannot
G2
read
there is a cycle of ACD.
B from C, sir.
ABC. So even
Once
in
a second.
G2 there's a cycle of ABCD.
A, B, C, and from C.
Okay, so it must come back
We
to the
cannot
initial.
read.
You should come back to A, right? Then only it will become a cycle. So you can see G2 indeed a DAG. So this is a DAG, directed acyclic graph. So the graphs are directed with no cycles sitting inside that graph. Okay. Now there are some facts about this DAGs. Okay. So what are the facts or properties about this DAGs? So the very first property is every DAG, so now I am referring directed acyclic graphs are simply DAG. Okay, so DAG means directed acyclic graph. So every directed acyclic graph has a vertex with, okay, now I use in degree 0. What do I mean by in degree 0? So I should have discussed degree previously. Okay, maybe I will leave it to you people. Not leave it to you people. As of now, I am leaving it on you. What do I mean by in degree? And what do I specifically mean by degree?
In degree may mean that number of edges coming to that particular vertex.
Good. Right. So before I start that, I need few more things to be defined, which is called degree. But
sir, the DAG which you described below was having in degrees, right?
Having
in degrees, C is having a degree in degree, and C is having basically two in degrees, and D is also having an in degree, B is also having an in degree.
I just said a vertex, one vertex.
Oh, okay. Sorry. I got it.
Okay. Not every vertex. Okay. Let me discuss this. Just okay. Let us just go back to some kind of flashback in a movie. It's like a degree of a vertex. So what is, this is also a term. So these are all terms in graph theory. There will be lots of terms coming into the picture, and you will be scared if you see so many terms and terminology
What is
in this
it?
graph. So what is a degree? So degree is very simple. It is the number of edges that are connected to a vertex. Okay. And to be more specific, degree is always related to undirected graphs. So when I say degree, it refers to a graph which is undirected, only for undirected. Okay. So then I don't need to mention this number of undirected edges. Okay. Simply I can say number of edges that are connected to a vertex is called degree of a vertex. Okay. So for example, v1, v2, as I said, for undirected I don't need to give directions. v3, v4, v5. Let's say this is the graph with 5 vertices and some edges. Now degree of a vertex means the number of edges that are connected to that particular vertex. So for v1, if you see, there is only one edge that is connected to v1. So the degree of this particular vertex v1 is 1. Similarly, v2, you see, there are 1, 2, 3 edges that are connected to v2. So the degree of this vertex v2 will be 3. Similarly, what is the degree of v5?
3.
v5, 3. 3 edges are connected to v5. What is the degree of v4?
So 2.
2. 2 edges are connected. What is the degree of v3?
3.
3.
3 or 2? 3.
3, sir.
3. See, this. Okay, so that's it. Degree of a vertex is this. Now, what do I call when a graph is directed? So this is very strong note. In a directed graph, we have in degree of a vertex and out degree of a vertex. So for undirected graphs, we had only one number that is associated to each and every vertex, only one number, and that number represents the degree of the vertex. So you can see each and every vertex has only one number associated to it. Was associated means connected to it or representing that vertex. Okay, but in directed graphs, for each and every vertex we will have in degree separately, out degree separately, and this strong node which I am referring to is degree of a vertex is not equal to in degree of a vertex, or simple word in degree plus out degree. So in degree of a vertex u in degree of a vertex u. So in a directed graph, you should never talk in this way. So I have in degree of particular vertex u is 2 and out degree is 3. So the degree of that vertex is 2 plus 3, 5. This is not allowed in a directed graph. And if you involve this, many theorems and properties will fail in the graph. So that there are many theorems on degree connecting degrees, number of edges and vertices. So these things will fail. And none of the scientists wanted that. Mathematicians and scientists wanted that. So they simply said, in a directed graph, there is no word called degree of a vertex. So this is a very big strong note. And even though however I say it is strong, most of the students will forget and they will simply do this. Okay. Leaving that. Now, what is in degree and out degree? So when in degree and out degree comes into the picture, this refers to a directed graph. So for a vertices, for a graph like this, so now that we are in the world of directed graphs, I think this is sufficient. Now, each please be on mute.
Yeah, sir.
Okay. So every vertex now will have two numbers to it, two numbers connected to it. One is in degree, another one is out degree. In degree is basically the number of edges that are coming towards you. Okay, coming towards you. So that means this pointing is towards the vertex. And similarly, out degree, now you can define it as the number of edges that are going away from you. So which says this thing. So this edge is going away from you, away from V2, and it's going towards V2. Okay. So now what you should do is, for every vertex, you should count the number of inward coming edges separately, and you should count the number of outward going edges separately. I know why people are Chinmay, Chinmay or
Yes, sir.
Can you please be on mute?
Okay.
Yeah, thanks. Now let's do this thing. Let's count. Let's start from V1. What is the number of inward coming edges to V1? How many edges are coming towards V1?
One.
One or two?
One, sir.
One. So you see only this particular edge that is coming towards V1. Okay.
So this in degree should include also directed graph, sir.
Huh?
So in degree, the inward arrow can be even for a directed line, sir.
Directed
So the
edges
in
only
degree
with.
can be
Huh.
no, sir, bi-directed.
It's bi-directed because see, as this is a directed graph, even though if I draw it like this.
My doubt is from V1 to V5 it is bi-directed. So here for V it is an in degree even for a bi-directed graph, sir.
See,
There is
bi-directed
one
means
direction which is directed.
It's like this.
Oh,
so this particular bidirectional says that there is an edge going from V5 to V1. Also, there is an edge going from V1 to V5. That's what bidirectional means.
Okay, sir.
Okay. Yeah. So now there is an incoming edge. Therefore, the degree of V1 is V1. Sorry, V1 is 1. What is, how many edges are that that are coming towards V2?
2.
2. So you can see.
2.
So the in degree is 2. For V3?
2.
2. So you see 2 are coming, this and this. For V4?
3.
3. This. For V5?
1.
1. Inward are slightly easier. Now tell me the outward. How many outward going edges are there for V1?
3.
2 or 3?
3.
3. This is 1. This is 1. Another one is sitting inside this. See, you see, this is a bidirectional. So there is an edge going from V1 to V5 also. Okay.
Yes.
So therefore, the number of outward going edges or out degree of V1 is 3. So similarly, V2?
1. 2.
1 or 2?
2.
Don't confuse, take your time and say
2, sir.
So this is an outward going edge from V2. Also, again, there is a bidirectional. This will also be like there is an edge sitting inside this. Now for V3.
1.
1 because only this edge which is going to be 4. V4.
2.
2 because see, this is 1 and this is the another one, but this is but not this. This is only one directional edge. It is only coming from V1 to V4. It's not going backward. Now finally V5.
1.
1.
So from V5 to V1 there is. Now this is how you compute in degrees and out degrees. So that's about degree. Degree is always related to an undirected graph, and in degrees and out degrees are related to a directed graph. Stating that, let's come back to this. Come back to the present. So what I said is every DAG has a vertex. So has one vertex, at least one vertex. I can say this. At least one vertex within degree 0. So I said this as a DAG. Is there any vertex which has in degree 0?
A.
Look at A.
Sorry.
A edges are only going outward. There are no inward coming edges to A. So the in degree of A is 0. So that's the property for any DAG. So you say, if you say a graph is a directed acyclic graph, then definitely there is a vertex with in degree 0. There is one vertex with in degree 0. And the next property is, which is not stated in class, I guess, but this I can state, and I can call it as a fact also. Every DAG will also have a vertex with out degree 0. Similarly, just like for in degree 0, there will also be a vertex where the out degree will also be 0. Can you give me in this particular example which vertex has out degree 0?
D.
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 D, sir.
D or B?
D, D.
D, sir. D for Delhi.
D, right? So
Yes.
this blue is out degree, and this red is the in degree. Okay, so that is about the DAG facts, and the main application of this DAG is the topological sorting. So what is this topological sorting means is, if you have some set of tasks aligned and you know that one task can be performed after a certain task is performed, and if you have these connections and I can able to sort the tasks in a sequential order depending upon their dependencies, that is what this topological sorting means. And even topological sorting has a direct connection to real life applications. Just like I said, if you have to do some tasks, continuous tasks or some courses, just like in the lecture sir has discussed about the courses, so you are doing this BS degree, so unless you finish your foundational courses you can't get into the diploma level courses, and then if unless you finish diploma level courses you can't go into the degree level courses. So there is some connections with foundational courses to the diploma courses, and from diploma courses to the degree level courses, and you have to order your courses how you should do the courses such that you will be able to finish all the courses in very less time. Okay, so that I will take. Yes.
So don't want to interrupt you, but it's already 10:30. Can you please take down?
Okay.
Sir, first
So
Yes,
the
sir. Is that
remaining
what?
topics, maybe we could have it in the next session. So like there'll be another session.
Right. There is another session, right? So we will cover it in the next session then.
So when is the next session?
I'm not sure, but it's supposed to be on Tuesday, right? I
So
don't know.
tomorrow there's a session.
Tomorrow, then tomorrow.
Sorry, sir. Tuesday is all with us.
Okay.
On Tuesday there's a session.
So
Okay.
could you do activity question 1?
Okay.
10
Okay.
point.
Before that, let me just end my.
So will you take the next session on Tuesday?
I don't think so. See, even today I luckily got a chance to take. So I'm largely involved in most of the stats 2 MLF courses, and I'm also in this mathematics for ES course. ES, not the DS, the other.
What is ES?
Electronic systems. Just like data science, we have started new degree
Yeah,
in
yeah, yes.
electronics.
Yes,
So in that we have mathematics.
Sir,
Could you please
small doubt,
take
sir.
next session, sir,
Yes.
on our request?
Huh?
Next session, sir, if you could take on our request.
Yes, sir.
That is highly
Request,
impossible
sir.
because I agree, but see, I have to look at for my schedule also, right? I maybe I can be open with you. Tomorrow I have a session which is MLF session. Day after tomorrow I have a session in stats 2, and Wednesday I have a session with my math CS revision session, which is a reattempt. So it is very highly for me to take 2 sessions in a day. So I can manage, but I will be like raat mein I will be just I don't know where I am sleeping. I will just be exhausted. So
Tuesday there will be a solve with us session.
no, it will not be solve with us. I will instruct instructor not to take the solve with us and proceed with this. See,
Tomorrow is
topological sorting.
also.
Only the topological sorting topic is pending, I guess. So that topological sorting.
So that BFS and DFS and their applications. That's the main things left.
Oh no! Why? How come I forgot that BFS DFS?
That's one, sir. If you could take the next session.
But actually, because it is a longer
For
topic,
that only.
tomorrow or on some other day, sir, because it's already.
Yeah, I agree. I'm not going to discuss that today, for sure. Even I didn't had my dinner and I can't
It's not
go
like
longer.
it will take longer time and you
Yes,
have
yes,
to
I agree.
college tomorrow.
Yes, I agree with your point. So,
And sir, this
is there any session scheduled tomorrow?
No, sir.
No. Okay, maybe I will ask the instructors to schedule a session tomorrow and continue. Okay.
Yeah, sir.
Okay. Maybe some 5-10 minutes, or maybe at max 15 minutes. I can take
Could
the
you
doubts.
take doubts? Yes.
Sir, I have a doubt from your
I
textbook,
have a
sir. Can you
doubt.
please clarify that?
In my textbook, huh? Okay.
Yes, sir.
Yeah.
I was solving the
Go,
questions and I got some doubt.
go ahead. Go ahead. See, I agree. There will be lots of errors in my textbook. That I am sure.
Yeah.
Yeah.
Yes, it is just on
Because
the
it,
questions.
hmm.
When you asked to draw the BFS tree and DFS tree of a graph, there weren't any solution to that. I didn't understand what tree means of a graph, DFS or BFS tree of a graph.
Okay. Can you give me the textbook? Sorry. Can you
Shall
give
I put the
me the
photo in
question,
the chat box, sir, of the question?
or you can read out the question? Yeah. Anything works for me.
Yes, just a minute, sir. I'll take this.
And yeah. As I got a chance today to talk about the textbook I have written, see, that was done in, I guess, 3 to 4 months time, and the proofreading is also not done because most of the students in the previous batch were asking for the book. Give us the book anyway, even though there are some errors. That's why we have given that textbook, and I think there will be some errors. I'm not sure, but if you find any errors, please do not scold me. Rather, please report it to me, and I will update the version.
Sir, I have put the photo in the chat.
Okay. Okay. Am I clear about my textbook?
Yes, sir.
And is it readable? First of all, I want to know, is the
Yes, sir.
textbook
I read your textbook,
giving
sir.
something?
Yes, it
Is
was
it?
good. I think some places I did find some kind of confusion. I'll let
Uh,
you know through email or mail.
did I went too much into technique? I felt I don't wanted to get into those in-depth uh, things, but anyway, I need a frank feedback on that particular textbook. If there are any negatives, definitely do let me know.
Yes, sir.
Can you
Sure,
get
sir.
a solution or something or anything so we could check our answers? Is there any?
Solutions are available at the
In the
end of
textbook
the
there is
pages, right?
solution. In the textbook there is solution for all the questions, but after this question there wasn't any solution.
Some questions.
Okay.
It's this question is also an activity question. I guess it's from 10.6 or 10.5. It's an
Acha.
activity question.
Yes. A few with time constraint. I said I took it from directly. Some are professor's statements only, and some are activity questions only. I'm not able to see A, B, F. Is that F above? Okay, whatever label it has, I'll just take the graph.
It is C, G, and D. G is above C, and D is on the right side.
Okay.
And E is below C.
E is below G and D.
Yes, sir.
So which
Yes,
question
sir.
is this, sir?
So this is uh, some activity question, as well as this is available in the textbook.
This is activity question, I guess, from 10.5 or 10.6.
Okay, 10.5
I'm
or
not sure, not very sure.
10.6. Okay, not
No,
sure.
which are
Even
the
I am not.
textbooks?
Okay, so we do have written some textbooks on these topics. So I have written a textbook on this graph theory part, and most of our instructors, even I have some contribution in week 1 to 4 qualifier part, and week 5 and 6 and calculus part, it was written by some other instructors, namely Shubham, Shubhajit, Subhashi, Sushmita. So there are some 3 different textbooks available for this particular course, which were written by the course instructors. Okay, please go through that.
PDF version is also available, sir.
Huh?
E-books.
These books, can someone give them where
There in the
this
supplementary content section.
supplementary contents? Yeah. Okay, you want BFS tree,
This
right?
question is from
BFS,
10.5,
and
second
BFS, sir.
question.
Both the trees I didn't understand.
Yeah, it is from depth first source question.
Okay. See, BFS and DFS are basically to traverse the graph. So it's like searching the
Yes, sir.
graph, right? These BFS and DFS does what it does is you start from a point, you start from a vertex, and you then traverse the graph. How do you traverse? Is like, see, some say I will start from a random point and I go wherever I can go, and
Yes,
I will
sir.
travel. And some say no, not like that. First of all, I will see where am I and where all places I can go. Firstly, I will observe that, and from that I will pick one place and I will go there, and then from there I will see where all places I can go, and then I will travel. So these are the two different variations, which one is called BFS and another one is called DFS. So the first variation which I discussed is DFS. I start at a point, and if I get an edge, I go through that edge and I reach to the next vertex. And from that vertex, if I found any edge which I didn't travel before, I will take that edge. And how long will I go? I will go till I reach a dead end. And from there, I will come back and I will move
Yes,
to the
sir.
next. So that is called DFS. And BFS is like very structured way. Like it is like it stands at a point. And you know what is BFS and DFS, right?
Yes, sir. I have read. Yeah, I
Ah,
understood both the algorithms.
okay. So what is it starting from A or from where?
E, sir. It is starting from E.
Okay, it starts from E.
Yes, sir.
Ah. So now I am starting from E. What BFS does is it will take E first at level 0.
Yes, sir.
Okay. So this is level 0. And from E, it checks what all neighbors available, right?
Yes, sir.
So what all
C and
neighbors
D.
C and B I can travel. Okay.
Yes, sir.
So that it will keep. So I can travel to B, I can travel to C. And these two vertices will come at level 1. And if you have read the textbook, then I have discussed something called levels and why these are called levels.
Yes, sir. Yes, sir.
Okay.
They help in finding the shortest path. So BFS helps.
Shortest ones, yeah. So BC, so E is done.
Yes, sir.
So now I have to go to B or C, whichever I prefer. Okay, E is done. Where shall we
Yes,
go?
sir.
E is done.
So now C, and we'll go for C maybe.
We'll go for C. Yeah. If no alphabetical order or no numerical order is given to us, I can go to anywhere. So I take this
Yes, sir.
path and I reach to C. So once I reach to C, so now I am here. Now I see the neighbors of C. So who all are the neighbors of C? B,
D
but
and G.
B is known to you.
D, D.
At E itself, you know B is there in your graph,
Yes, sir.
right? That is there.
Yes, sir.
But what are the newly found vertices?
D and G.
D and G. So D and G, you know, you are here and you newly figured G and D. Right? So that comes in the level 2. So this is D and G, level 2. So now this is done. Okay. So I will move forward in this, or what I will do is, as this is visited, done, right? So this is done.
Yes, sir.
And now what I will do is, from here, I'm still, see, if you know this in lectures also, there is something called queue. Sir has used
Yes,
queue
sir.
and stack, right? You
First and first out, I guess.
first in, first out. So now if I write it, E, maybe C and B came in. So these are the first vertices you observed. E you
Yes, sir.
observed, from at E you observed C and B, and you went to C. So E is done. So you went to C, and then B is already observed. You observed new vertices GD. Then C is
Yes,
done.
sir.
Now B's time. So now you should
Yes, sir.
move to B. Now you are at B, and you explore what are the new vertices you are seeing there.
Yes,
What
sir.
are the new A and F you are seeing? You
A
will be
and
seeing
F.
A and F, right? Based on these edges. So now those A and F comes below B.
Yes, sir.
Right? And A and F also comes in the level 2 only. The same level. Okay.
Right,
Now
sir.
B is done. B is done.
Sir, actually, I
Next.
had lost. Are you explaining the concept or are you
No,
just
no,
hearing
no,
this?
no, 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 no. People who are still waiting that I am explaining concept, no.
Okay,
Or
sir.
like
That's right.
tree diagram.
Huh?
Or like a tree diagram.
That's why they are called DFS trees and DFS trees. So whatever I am going to draw will eventually be a tree.
Yes, sir.
Okay. So now G. So from B I am done at B and I have to go to G. This edge is done. This edge is done. This edge is also done. So now at G I have to explore D, which is already explored. I know that D is there in my graph, right? There is no new
Yes, sir.
stuff I am going to explore. G is done. Then I have to go to D. I'll go to D. Why I will go to D is because, see, if there is something connected to this, you haven't seen this like a black space. Until and unless you go to D, you don't know what is around D. So that's why we will
Yes,
go
sir.
to D. Even though you go to D in this particular case, there is nothing new.
Right, sir.
Right. So if you had played games like treasure findings, or recently I have played one game. See, everything will be cloudy. You have to build your empire. So these kind of empire building games, right? So
Yes,
you
sir.
will be given some small space, and you have to upgrade your level and then explore new places, right? So that's how
Yes,
this
sir.
does. DFS does in the same way. Okay. So this is G is done, D is done, this is done, this is done. So now I have to go to A. Once I go to A, still, even though I reach A, there is no new graph that is connected to A. So whatever we have
Yes, sir.
explored, that's the only graph. So this
Hmm.
is done, and finally F will also be. And this is my BFS tree.
Sir, so we won't connect like A and F again in this tree.
No, A, why to connect A and F?
Okay.
So you already explored, right? You don't need to see this edges refer. You reach to B and you explore A and explore F. Once you
Okay.
reach A, you no need to explore F again. F is already explored.
Okay. Okay. Got it, sir. Got it.
Okay. Yeah.
So,
And
so
these
could
are
you
called
please,
trees. Okay. So read the
Okay, sir.
definitions of trees.
Yes,
so
sir.
could you please take activity question 10.1?
Yeah. So
Yeah, can you
DFS
just
is
hold on?
also.
Let sir explain the
There is
DFS
no
tree part.
starting
Yeah.
point.
So let me just do the DFS also, and I will take activity. Okay. So I will start
Sir, there
from
is
E.
no specific starting point.
There is no specific.
Sir, there is no specific starting point. We can start from anywhere.
No, no. See, this is given. The starting point is E. So we started at E. And the starting point will matter. If I change the starting point, your graph might be little different.
Yeah, that's I'm saying.
So we started from E. So in the question, it will be given where to start. Starting node. We call it as starting node. Okay. And what this DFS does
Okay.
is,
Okay.
this is something like uh, you go as deep as possible, as depth as possible. So you started from E.
Yes, sir.
You don't look for the neighbors. You got an edge. You travel along that edge and move to the next vertex.
Yes, sir.
And from there you move to the next vertex. And from there you
Sir,
move to the next vertex. Yeah.
sir, then there could be multiple kind of DFS trees, no, sir?
There can be, if order is not mentioned, there can be multiple. See here, one possibility is from E it can go to C, from C it can go to D, from D it can go to G. So once G is there, you see, once you are at G,
Yes, sir.
you can't go to C now. See, C is already
Yes, sir.
explored. You came from C. So what you do
Yes,
is
sir.
that's the dead end you reach. You just have to come back to D, come back to C, and from
See,
C you
and
see
then
is
again
there
start.
any unexplored vertices? Yes, there is. There
Yes,
is
sir.
an unexplored
B.
route B side. So now it is like U G D C, from C there is B. Okay, and from B you can go to A, and from A to F, or F to A. Anything is fine. So from B to A, and so this is the DFS. So what is, see, this is a greedy algorithm. We call DFS as greedy algorithm. It is very greedy that it goes, the moment it gets a path to the next vertex, it takes that path and moves to the next vertex. That's how DFS works.
Sir,
Okay. Yeah.
similar in the similar question like this in your textbook, you asked like if there is a DFS tree in this on a particular graph, what means between two edges, can there be an edge or not? Like between two vertices, can there, which two vertices can there be no edge?
That's a different topic, which I don't think right now possible. Maybe I'll
Okay,
ask
sir.
the other instructor to take this. Yeah, one more
Okay,
doubt
sir.
on activity question.
Yes, sir.
Aditya.
Activity question
Yes.
10.1, sir. So the resistors combination question, I'm not getting the logic behind these.
See, maybe you can skip that question. Even we don't wanted
Yes.
to do that, but for the time being, you just skip. We have given multiple edges in the same graph, right? Is that
I didn't understand that. Like, what is the logic behind each picture? What is happening? Why is there connections between two edges? And what do these connections mean? I tried
ah?
Yes, sir.
drawing it and
Okay,
checking.
okay, okay. I
And
understand.
also in the fourth question in the same set, I'm not able to figure out if these are, unidirectional or undirected, what it is.
Is that so?
The
It is a
fourth part.
directed graph.
Okay, maybe I can skip 10.1 saying you just ignore that question. We are trying to remove that. That's a confusing question which we don't want to encourage.
Okay, sir.
Maybe
And in the
10.4
first
I can.
question,
Yeah.
in the first question in that, there is a mention of V is equal to 1, 2, 3, 4, and there's a set also given. 1, comma 2, 1, comma 3, 1, comma 4, 2, comma 3, 3, comma 4. So what's the point of giving V is equal to 1, 2, 3, 4 in that question? Because I just used the sample space they've already mentioned there, and I marked question number 1 because some options I ruled out. Basically, I didn't get the answer, but I ruled out the other options. I didn't really understand these questions. It's just, what my gut says is right. I just selected them. That's what I did. Is there
Okay, that
some
is what.
understanding that should be there in these? I'm not understanding that.
No, 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 no. So I do agree. 10.1 is slightly not needed in this particular week, or maybe in that particular activity, especially. So you can ignore that question and you just go ahead.
Okay, sir.
Sir,
I hope it
I
won't
have
come.
sir, I have just two more questions from your
Two
textbook, sir.
more.
Can you clarify if possible?
No, right now it's highly impossible. Maybe I will give you my mail
Okay,
ID.
sir.
You
Yes, sir.
can send
Please
a mail.
share your mail ID, sir.
Okay. So
Share in chat box.
everyone,
Yes, sir.
but don't ask me the reviews of any movies or something. Let's keep it technical discussions. Okay.
No, sir.
Yes, sir.
If you're, or don't ask me any questions or inside stuff. Okay, I can. My ID is already all. I guess it's available on.
Sir, where can I find like questions like this in like a structured way, like a topic wise? In your textbook, you have given like 19 or 20 questions.
Where is the
But
textbook?
whenever I go online and search for like graph theory problems, I'm getting like all programming problems instead of problems like these.
Mm-hmm. See, there is a
So,
book named with Bondi and Murthy.
uh, What is the name, sir?
Bondi,
Bondi.
Bondi and Murthy. Its PDF is available online.
Okay, sir.
Okay, so you can get the PDF of it, and it is more of mathematical problems. You will see more of
Yes, sir.
mathematical problems.
Yes, sir. Even I went through other graph theory books, pure maths graph theory books, but those questions also those were more involved in proofs and stuff, not questions like these, which are.
Even in this textbooks also you will be seeing proof questions also, but ignore those questions and solve this uh, finding something, finding vertex color, finding vertex
Okay, sir.
cover.
So,
Yeah.
Yes,
so
sir.
week 12 does not have a graded assessment, right?
Uh, I'm not sure.
Yeah, it's yellow.
Week 12
Yeah,
is just
it's
Week 12 is just revision session. It will not have
Okay,
any
So
graded.
it's
I have one more doubt, sir.
front cover is yellow.
In the end term portions, what is the end term portion? Is it 9 to 12 or from the beginning?
See, it should be from beginning, and 33%, 33 to 40% covers graph theory.
33 to 40%. Okay.
Yeah.
So more weightage for graph theory, but
it's from week 1 to week 12, week 11.
okay. So do we have to emphasize on calculus or is there any tips, sir?
Emphasize on calculus.
Calculus part, like the differentiation part, which is like,
Yes.
relatively new in this.
Yes.
So will we get more questions from that or how is it, sir?
Okay,
What
maybe
should we
I can tell
prepare?
you. I can tell you approximate things: 40, 40, and 20. So week 1 to 4 you will get 20%, and week 5, 6, 7, 8, 9 you can get some 40%, and graph theory 40%, something like this.
Okay, sir.
Okay.
Okay, sir.
So in
Thank you.
that
Sir, you shared your
calculus
mail
part,
ID, sir.
I shared, right? I
Uh,
think I
it
have
it is
shared
not
already.
No,
there in
sir,
the
we
chat,
didn't
sir.
get, sir.
Yes, sir.
Okay. Sorry, I shared.
So it's JB Murthy, na, sir? JB Monin Murthy.
Bondi and Murthy.
Sir,
Hmm.
sir, can you say how this answer happened? Practice
Sorry.
assignment
I can't hear you. Is
one.
it me or everyone the same?
No, sir. Even
Can't
I
hear.
can't hear properly.
I'm writing in sir chat box. Okay, sir.
Okay, just put it in the chat box. Okay. Yeah, this is my mail ID. As I requested, please use my mail ID only if and only if it is needed, and that too in my textbook feedbacks and any doubts related to mathematics course.
So
Okay.
Yes.
how you gonna cover the application parts?
How?
The application parts of BSF and DFS.
That's what I said, right? I will talk to the instructor
Yeah,
and ask them to
it's
take a
needed.
session. Yeah.
It's very needed.
So yeah, we will have a session. Okay.
Sir, are you also a
Okay.
part of this BS degree program, like student?
No, I am not a student.
Okay. You look very young in the photo.
That's my post graduation photo, which is 5 years ago, maybe not even
Oh,
five,
okay.
maybe 6 years ago. Okay, maybe I didn't introduce myself, right? Like I introduced it at the start, but I have done my masters in mathematics from IIT Madras
Okay.
in 2018 to 20. And after 2020, I have joined this IIT MBS degree. From then, it's been 3 years working closely connected with IIT MBS.
Okay.
Initially, I took sessions. The first, second terms, I was one of the course instructor in mathematics course only. Later, I moved to statistics. Right now, I am in machine learning foundations, which is diploma course.
Are you doing anything apart from this?
Apart from this work,
Yes.
you
Sir,
mean?
I have put it in chat
Yes,
box.
yes. Yeah. I am trying to do PhD. Right now, I am doing two courses as a student in IIT Madras, wherein which it helps me to join PhD in IIT Madras. So that's the thing I am doing right now. So that is what I said, right? I am slightly uh, overloaded with my work, so I can't promise you to take another session, but I don't know. So what is this? Which one is the doubt? Practice assignment question 1. Is that the doubt?
Yes, sir.
Or someone posted?
No,
Okay,
sir. Yes, sir.
that's the
Yes.
text. Okay, what is that question about? Can you tell me what the question is about? Okay, I have to open this. Can someone tell me what is practice assignment question
Taking, sir.
1?
Yes, just
So,
so it is a DFS tree question. So it's
and
the
which
same
is
question, which cannot be an edge.
okay. So maybe we will do that in the next session. Allows the
Yes.
interested to
Original
relate.
path, sir. Original path. I
Yes,
didn't get
yes,
to know which one is
yes,
original
yes,
path.
yes. That's the applications of this DFS. That will be discussed. Okay. So with that note, uh, let's end this session today. Hopefully, I will meet you guys
Thank you,
sometime in
sir.
the future.
Thank you, sir.
Okay.
Thank you, sir. Good
Thank
night.
you, sir.
Thanks.
Thank
Thanks a
you, sir.
lot, and have a good
Good
day.
night, sir.
Thank you, sir.
Bye.
Thank you very
Very
much,
much,
sir.
sir.
The
Thank you,
concepts
sir.
are very much clear, means in this session.
Okay.
Yes,
Thanks.
sir.
Thank you. Thank you so much. Mahesh, if you are
Today's session
there,
is very much clear.
okay. Thanks. Mahesh, if you are there, please stop the streaming and end the session. Okay. Thanks, guys.